Eddie said it. What'd you say? It is x. Very good. By definition, you could look at domain in a couple of different ways. Official textbook definition, possible values of, Eddie said it, x. Possible values of x. Or you could say that they are values that x can assume. Possible values of x. That's a very algebraic definition. You could also apply this graphically. I often like to describe domain to my students as just the space that a graph takes up on the x-axis, for the horizontal axis. So on a graph, it is the space that the curve or line takes up on the x-axis. Domain is a statement that describes that. When we get to rational expressions in particular, you get two more terms. The first word there would be vertical asymptote. That is a vertical line that the graph gets infinitesimally close to, but does not touch. Horizontal asymptote is just a horizontal line that the graph approaches at its ends. Infinitesimally, I have to practice saying it. A little bit of background information. Your homework tonight is the worksheet that you grabbed when you walked in. My goal for today was to give each of my classes two techniques, not just one, but two techniques for finding domain. And in reality, the warm-up took us longer in all of my classes than I anticipated it would, which is fine. I move at your pace. We've discussed this. So chances are you're only going to get one technique today. The technique you're going to get today is graphing. So we're going to focus primarily on this definition for domain today, the space that the curve takes up on the x-axis. So these are our examples off to the right. When you go through your homework tonight, you're going to be producing graphs that look like this. All you do is type them in your calculator. It's pretty easy. I do have a question about that, however. Does anybody not know how to, like, for instance, on this first example here, that first example there, I typed that equation into my calculator and got this graph right here. Does anybody not know how to do that? Everybody knows how to go into y equals, type in an equation, get their graph. Yeah, okay. That's what you're going to do tonight. And if you look at the assignment sheet, it gives you some pretty clear directions on what I expect to see. You're actually doing this worksheet on separate notebook paper. The notebook paper part picks up at the bottom of the assignment. You'll see at the bottom of the assignment, there's no pictures. It's just equations. The equations you have to type into your calculator. Sketch the picture that you see by maybe grabbing some points off of your table of values, and then identify the domain. So when you come in tomorrow, your homework is going to look like these examples right here. Everybody clear on that? Of course, you'll have an answer. The mission in that assignment is to calculate the domain. Today, like I said, I'm going to show you how to calculate the domain of a function just by looking at its graph. That's what we're doing today. I'm going to start with an easy one. I'm going to start right in the middle of this chart here, underneath domain of a radical expression. I'm going to draw a picture. You don't have to draw this. This part of the lesson, purely for your visual entertainment. You'll like this. This will be moderately entertaining. That's a stick person. That stick person is you. You imagine you're like standing two-dimensional on my note sheet right now. Okay. I am going to right now shrink you a little bit because I drew you too big. I'm also going to make you dizzy. Ready? Ah! Okay. Enough of that. Now I'm going to make you jump up on the x-axis. everybody see where we're looking? Right now we're examining this particular graph to find the domain of f of x equals the square root of x minus 2. So we're identifying that domain. Right now you are standing on the negative x-axis of the coordinate plane. Everybody see where you're at? Imagine you're standing there. And as you walk along the graph, you're going to walk along the x-axis, because what you're trying to decide is the space that the graph takes up on the x-axis. You're trying to figure that out. So just stand there for a second. This is you standing here. I'm going to say maybe you're standing at, it looks like you're standing at, what is that, like -8 right there? So that's you standing there. I want you to look up and look down. So look up, you're standing on the graph, you look down. My question to you is, do you see any points either above you or below you? Do you see any parts of the graph, any parts of the curve? Do you? You don't. So there are no domain values at -7. -7 is not a place that our graph occupies. So it can't be part of our answer. So I'm going to have you keep walking. I'm going to move you over to, like, I don't know, maybe to -3. So you're standing at -3. And you look up and you look down. And my question to you is, do you see any pieces of the graph there? Do you? Do you see any pieces of the graph there? No, there's none. So our function isn't defined at that point. Let's move you over to the origin. So you look up and you look down. You see pieces of the Cartesian plane. I mean, mainly you're going to see the y-axis, the positive y-axis. You'll see the negative y-axis. Hey, you'll even see the origin, right? But will you see any points on our curve? Any points associated with our function? You're shaking your heads. No, you will not. Can anybody tell me where you would finally start to see some points? At 2, very good. Tammy said it. Right there at 2, you would finally see your first point. And we have to use our imaginations a little bit. You know that your calculator doesn't put this, but you know that there's an arrow there, right? You know that. So this graph starts at 2 and keeps going. So if I put you over here at like 8, there's points hitting you right in the chest. Oh, getting barraged by points, you know? If I put you over at 10, you'll still see points. If I put you over, oh, whoops, that's not you, that's the arrow. If I put you, bless you, if I put you over at like, if I could, you know, over at like 15 on the x-axis, you would still see points. So what we learn out of this is that this graph starts at 2 and goes on and on and on forever and ever and ever. That statement that just came out of my mouth is a statement that describes the domain of the function. I'm going to say it again. This graph starts at 2 and goes on forever and ever and ever. If you can't understand the notation throughout today's lesson, at the very least, you could write me a sentence that describes the space that that graph takes up on the x-axis, and that's the expectation. I want you to be able to describe for me the space that the graph takes up on the x-axis, because that is ultimately a description of the graph's domain. So, because we don't like to write big, long sentences like that, we, math people, have a shorter way of writing it. This graph started at 2. You always work from smallest to largest. So this graph starts at 2. So you put a bracket and a 2. And then it goes on and on and on forever and ever and ever, which means that it goes towards positive infinity. So you put a comma, a positive infinity, and because we only approach positive infinity and don't actually ever get there, well, hey, because it's infinity and we can't, you have to put a parentheses there. Notice that there was a bracket around the 2 because the 2 is an actual point. It's a solution for the graph. You could plug 2 into this function. 2 minus 2 is 0. The square root of 0 is 0. 2 comma 0 is your first point. So it starts at 2 and heads towards positive infinity. Questions about that? If you can't understand the notation, you can always write me a sentence. What's up, Eddie? It actually is. It actually is. Yes, it is. Yeah, that's not like a Mrs. Lucas, like she's just weird about this rule. That's like a real math thing. All right. already moved you over to what we were trying to describe as x equals 15, but now we're going to start on the next equation. So this is you're jumping. Settle down over there. Okay. Right now I'm going to put you on the negative x-axis, and you're going to go for a walk. Again, sometimes you need to use your imagination. Remember that there are arrows on the end of that curve. So now, right now you're standing at like -7. You look up, you look down. Do you see points? You could just nod your head. Yeah, you're all sitting nodding your head. Yes, very good. So you see points there. I could put you at -3. Do you see points there? Good. What about at the origin? Weird stuff happens around the origin. You always want to check the origin. Yeah, there's points there. Good job. What about at 5? Yes, good. Did anybody, here's a hard question. You ready? This one's a little more challenging. Is there anywhere I could put this little stick person, you? Is there anywhere I could put you where you can't find a dot or a point associated with your function? Is there anywhere I could put you where there would be a space or there's no points there? Is there anywhere I could put you on the x-axis where you wouldn't see a point? What do you think? You're all shaking your head now. Good job. So basically, you're all right. You know, you're all saying like, hey, this graph lady goes on forever and ever and ever. I could walk anywhere along this x-axis, and I would see points there. That's great. Now we just have to figure out how to write that sentence in some math speak, in some symbolic language. What we're basically saying is, well, yeah, this thing goes on forever and ever and ever towards positive infinity, but also goes on forever and ever and ever towards negative infinity. Notice I use parentheses around things that I cannot touch. Can't touch infinity because it's infinite. So we go from negative infinity to positive infinity. Bless you. Questions about that? I'm going to jump up to the top. And by I mean you. Here's you. Whee! Okay. And we're going to do f of x equals 2x cubed plus x minus 1. Again, sometimes you have to use your imagination. I'm going to put arrows on the end, right? And, you know, I said always check the origin. So there's you standing at the origin. If you're standing at the origin right now, you look down, you see some points. Actually, a point. If you see multiple points for one x value, hey, that's not a function, right? Fails the vertical line test. So you look down, you see a point at 0, right? If you go to the right just a smidge, you see a point. If you go to 2, you look way up there, but you see some points. My question to you, my very smart period 6 college algebra class, is if I put you all the way over at 10 and you look up, would you see points? I see people nodding for the most part. Some people are like, giving me like the, what's that, the furrowed eyebrow, right? Or, I don't know, lady. Okay, so eventually, yes, you would. Remember, these arrows kind of tell us that this graph, I'm going to draw something, you don't need to draw it. This graph goes up and out forever and ever and ever. So they'd be way up there, but they'd be up there. We would see points up there eventually. So you got to kind of use your imagination a little bit and predict where this thing is going to go. Being good at math is a lot about making some predictions. So we could predict that this graph will have values. If you're really worried about it, you could always scroll in your calculator, scroll through your table of values and see that there would be indeed points there. We would take care of that maybe more tomorrow. We'll show you how the calculator can help you with this. So yeah, if you look right now, as I head towards 10 or 100 or 1,000,000, I would see points there eventually. Same thing on the other side. Eventually at -10, -100, -1,000,000, we would have points there. You could plug anything you want into that function. True story, look at it. You can pick whatever number you want. You're going to get something back out because we can plug any number in for x. The domain of this graph goes from negative infinity to positive infinity. And the last one. What you're going to notice about this graph is that doesn't it look like it's in 2 pieces? This is the primary sort of shape that we take care of in this chapter, shape for a rational function, where we kind of get pieces to our graph. What you're going to notice is that right around 3, you're not going to see any points. So let me grab you for a second and be a little bit more deliberate about that. So there's you coming back down to our last example. Right now you're standing at like -10. And you're walking along your x-axis, and all of a sudden you're like, ah! And you like plummet to your doom because there's no points there. The ground sort of falls out underneath you. It's kind of like if you come to the edge of the cliff, you look down, there's like nothing there. And then all of a sudden you like pop back up here again and you get to the other part. On the other side of x equals 3. And then you slide, whee, like down. So you would see some values there after we cross x equals 3. What we get is this idea that this graph is defined in 2 pieces. It starts at oh my gosh. Okay, so it starts at -infinity. And something weird happens at 3. And I can get really, really close to it, but I can't actually touch it because there aren't points there. I fall down. So it gets to 3. We don't touch it. You can't touch 3. Do you see why? Look at that. Oh, you can't divide by 0. So we actually can't get to x equals 3. There's no points there. And then, all of a sudden, like I said, we get to this second piece. See this big U here? That means in union with. U means union. So you have the first part of the domain in union with the second piece. The second piece that, you kind of just slid down right there. It starts really close at 3, doesn't actually touch it, and then heads towards positive infinity. Questions about that? What's up, Brooke? Okay. So, today we learned how to identify the domain of a function just by graphing. Tonight on your worksheet, you're going to see that the graphs are given to you. It also asks for domain and range. You don't need to do range because we didn't do it in class today, nor are we going to. All you're going to do is look at the graph and write the statement for the domain. You'll notice at the bottom of the worksheet, there's no graph given to you. This is where you go to your notebook paper. You graph the equation in your calculator, draw me a picture of what appears on your calculator. You could go to your table of values if you need some more definitive points. Draw me a picture of those graphs. It doesn't have to be beautiful, it just has to be done. And then write the domain associated with that. Yes?